So in looking at the drag characteristics on a cylinder, it turns out that the nature of the boundary layer plays a very big role in the drag coefficient on the cylinder. So what I'm going to do is draw two different cylinders, one with a laminar boundary layer and the second one with a turbulent boundary layer, and then we'll look at the drag coefficient and the characteristics. Okay, so what we have drawn here, on the left we have a cylinder that has a laminar boundary layer forming from the front stagnation point. And then the cylinder on the right, we have a boundary layer that becomes turbulent. And so it could become turbulent due to the Reynolds number. It could also become turbulent if you were to put surface roughness on the front of the boundary layer. Again, that would depend upon the Reynolds number of the flow over the cylinder. But if you have the turbulent boundary layer, it will have an impact upon the separation characteristics from the body. And so if you recall, we had the lecture about how pressure gradients are very important to the performance of boundary layers. And you can have either favorable or adverse pressure gradients. In this case, you would have an adverse pressure gradient on the cylinder, and so the flow in the laminar boundary layer has less energy, I guess you could say, or less momentum right along the wall region, and consequently you get to the zero shear point earlier than you would with the turbulent boundary layer, which is what we have on the right. So the implication of all of this for drag characteristics, if you look at the drag coefficient for a cylinder with a laminar boundary layer, the drag coefficient is 1.2. Now, if we look at the drag coefficient of a cylinder with a turbulent boundary layer, the drag coefficient is much lower at 0.3. And the reason is because the boundary layer is energized and it's able to make it past where it would normally separate and continue on the body, and then it separates aft of the 90-degree point, and that results in a narrower wake, a lower form drag. And so that is a characteristic of the cylinder, and so I just want to make a comment about that. So what happens, we have less drag due to the fact that the boundary layer is energized when it is turbulent. And this is actually, I'm sure you're aware of this. If you're not, it's the reason why golf balls have dimples in them. And what the dimples do is they cause the boundary layer to transition. And when it transitions, it goes from laminar to turbulent. And so it'd be the dimples on the front of the ball that are the ones that are causing the effect. But it's basically surface roughness. And that causes the boundary layer to become turbulent, and consequently the separation is much further downstream than it would be if you had a laminar boundary layer on the golf ball. And this causes the golf ball to travel much further than if you had the laminar boundary layer on the golf ball. So that's something that we use for those of you who are avid golfers. You can now explain to your golf partners why the golf ball travels as far as it does. So there we have something from sports that can be applied to fluid mechanics. Now, what I'm going to do in the next slide here is I'm going to plot the pressure distribution around the cylinder, and that will provide a little bit more information in terms of why this process is occurring. Okay, so what we have there, I've drawn on an inviscid pressure distribution. So we have CP plotted in the vertical here, and that is the pressure with respect to the free stream pressure. Theta is the angle with respect to the free stream velocity, going from 0 to 180 degrees. So we're going from the leading edge over to the back of the cylinder. 90 degrees would be up here. And I've plotted in the inviscid pressure distribution. Inviscid would be what you would get out of potential flow. And we haven't done that in this course, but you would basically do superposition of elementary solutions and then put them together and they satisfy, you use the Laplace equation for that. And you can then compute the flow over a cylinder, and so we can come up with an analytic expression for the pressure distribution around a cylinder. Now, in reality, what happens, no flow is inviscid, because inviscid would assume that we have symmetric streamlines going around like that, which we don't. Because we have separation. Now in the case of a laminar flow shown in red, we have the separation is up around 80 degrees. So someplace up in here is when you start getting into the separation zone with the boundary layer starts to lift off. And then for turbulent flow, it would be up a little higher around 120 degrees where you start to encounter separation. So again, this is just a little bit of a artist conception of it, a very poor artist conception. Please do look in your textbook or other things in order to see the pressure distribution on cylinders. But the main point is you can see that when you have a turbulent boundary layer, it more closely approximates the inviscid characteristic where you have no separation on the cylinder, and consequently with lower pressure drag on the back of the cylinder that or lower you don't have as much of a form drag on the back of the cylinder, and that reduces the drag coefficient for the turbulent boundary layer. So that is flow over a cylinder. What we're now going to do, we're going to move in and look a little bit at streamlining. So streamlining is something that we use in order to reduce the drag on objects. And so let's just look at an example. So let's assume that we have a cylinder, and I'm going to say the thickness is T, but it's also the diameter of the cylinder. The chord, sometimes we will use C to denote the length, but that is a cylinder. So we could say T over C is equal to 1. And then if we have an airfoil, I'm going to try to draw a symmetric airfoil. That's not perfect. Again, the thickness would be somewhere here. The chord is the length of the airfoil. So let's say this airfoil has a T over C of 0.15. NACA 0015 would be an example of something like that. Looking at the drag coefficient, we saw for the cylinder about 1.2, and if you look at the drag coefficient for NACA 0015, it's actually 0.061, significantly less. Now, granted, it is thinner, much thinner than the cylinder, but there are other things going on, and mainly what's happening here, the boundary layer is very different on these two bodies, obviously, especially in relation to where it may separate from the body. When you have streamlining, the purpose is to cause the flow to go all the way around the body without separating. So that's really the goal that we have in drag reduction. Sometimes you do get a little bit of a separation zone down in here. Now you contrast that to the cylinder, and at 1.2 that would mean that we have a laminar boundary layer, so we separate around 82 degrees. We get this massive wake forming and form drag coming there. So what we're going to do next, we're going to take a look at some video clips showing us a flow over different bodies, some of them bluff bodies, some of them streamline bodies, and then we're going to measure the wakes, and we're going to compare that to the drag coefficient just to kind of highlight the advantages of streamlining. Before we do that, however, I should make the comment that essentially a streamlined body for the same frontal area will have a much lower drag coefficient, and so that's really one of the main things with streamlining. So for the same frontal area, drag on a streamlined body is much less. Okay, so let's move on and take a look at the videos. So what we start with is flow over a cylinder, circular cylinder, diameter D. We're going to look at an ellipse. So here we have an elliptical body, thickness 1.15 D, so it's thicker than the cylinder. And finally, this is an NACA 0015. It's thinner, 0.77D is the thickness. Now let's take a look at the wake widths occurring on these bodies. So here we have the cylinder wake width. I just crudely measure it, 2.1D. Here is the ellipse, wake width about 0.77D, thinner than its thickness. And then finally the NACA 0015 wake width about 0.28D. And that's a fairly crude estimate with just me looking at the video and trying to estimate what those values would be. Let's write those down and compare them to the drag coefficients for these objects. Okay, so there we have the three objects that we've looked at in the video. We had our cylinder, wake width we said was 2.1 times the diameter of the cylinder. The ellipse, wake width was 0.77 times the diameter of the cylinder, although it was a thicker body at 1.15D. And finally the NACA, we estimated the wake width about 0.28. That was fairly far downstream of the airfoil. For a thickness that is on the same order of magnitude, 0.77 versus the 1D for the cylinder. So looking at the drag coefficients now, so we've already seen the cylinder. The cylinder has a drag coefficient of 1.2. For the ellipse that we looked at has a length to thickness ratio of 5, and with that experimentally those have been determined to be 0.25 would be the drag coefficient, so significantly less than what we saw with the cylinder. And then going to the NACA 0015, we saw 0.06, so really low. And part of this is due to the fact that we have a reduction in the wake width, but it's also due to the fact of the nature of the boundary layer forming around the object. And consequently the skin friction characteristics that would result. But obviously NACA airfoils have been designed for high lift and low drag, always what you're after with those. But what this highlights is that the width of the wake does have a fairly big impact upon the drag characteristics, and consequently streamlining is used in order to reduce the drag on bodies.